Dear students, welcome to this lecture on digital logic and system design. Today we are going to start a fresh unit, and in this unit largely we will talk about the combinational circuit. Before we go on to the actual circuits, let us devote a slide or two for a very important gate which we have already introduced, but it needs some more attention because this gate is going to be used as one of the primary elements in some of the combinational circuits, and they are the exclusive or and the equivalence functions. If you remember, equivalence functions are basically exclusive NOR functions. There are several names given to this function because of its utility. So it is basically, equivalence function is basically an exclusive OR followed by a NOR, right? So exclusive OR and equivalence, denoted by this symbol and this symbol respectively, are binary operations that perform the following Boolean functions. X exclusive ORed with Y is xy dash plus x dash y, as we have already learned from the truth table of the exclusive OR gate. Exclusive NOR gate, on the other hand, is xy plus x dash y dash, once again from the truth table of exclusive NOR that we have seen earlier. It may also be noted that they are the complement of each other. If you complement this thing as whole, you will get this, and if you complement this thing as whole, you will get this. You can do it for yourself by applying De Morgan's theorem and distributive law. Now the two operations are the complements. Each is commutative and associative. Both of them are associative as well as commutative, right? By commutative we mean x exclusive OR with y is equivalent to y exclusive OR with x. Similarly, x exclusive NOR with y is equivalent to y exclusive NOR with x. Similarly, associativity, a function of three or more variables, can be expressed without parentheses as follows using associative law. A exclusive OR with B, this whole exclusive OR with C, is equivalent to A exclusive OR with B exclusive OR with C. So this can be written as A exclusive OR with B exclusive OR with C, right? So likewise, we can write any number of variables without parentheses. Had there been four variables, I could have easily written A exclusive OR with B, exclusive OR with C, exclusive OR with D, and so on. Now, when it comes to realization and realization of exclusive OR, let us take it. Then from the very Boolean expression that we have seen here, x bar or x dash comes here and this is y. So I get x dash y, and over here I get xy dash. When I OR them, so x exclusive OR with y is what I get, x dash y plus xy dash. So this is the straightforward implementation in the AND OR form that we are already familiar with. But over here, if you see, it requires 5 gates in all, right? One OR gate, two AND gates, and a couple of inverters. If I try to get these inverters using a NAND gate, then the complexity, the hardware complexity will even go further up. So 5 gates are required this way, provided that the complement of the functions are not given. So let us look for an alternate. This is the alternate implementation of exclusive OR, but with 4 gates only. So the hardware complexity comes down, and I have joined them in such a way. Let us analyze it and see for ourselves. This is xy, so I'll get x dot y whole dash because this is a NAND gate, right? Now over here, I'm getting x dot y whole dash or and x, which is coming here, whole dash, because this is a NAND gate again. Whereas on this side it will be x dot y dash whole dash, this one, ANDed with y and whole dash. Sorry, so what do I get here now? That I've analyzed here. Basically, this thing x dot y whole dash dot x, and this thing entire thing complemented dot x dot y dash dot y whole dash, right? And this entire thing again complemented because of the NAND function. So this can be written as x dot y whole dash dot x. So I'm applying De Morgan's theorem. The first stage of De Morgan's theorem will be the complement of this plus complement of this. Now since this is already complemented, so I'll get its true form, right? So x dot y whole dash dot x, plus x dot y whole dash dot y, right? So first step of De Morgan's theorem. Let me go on applying De Morgan's theorem again. So now you must start feeling the importance of De Morgan's theorem. How important is the De Morgan's theorem, right? In the next step, I'll open this one up. X dash, this will be x dash plus y dash dot x will be there anyway, right? All right. Whereas on this side, it will be x dash plus y dash. So when I open this one up, this and will become or. So and each one of them will individually be complemented. So it will be x dash plus y dash dot y, right? So this will be the step from this one. So now in the next step, we will apply the distributive law. When I apply the distributive law, this becomes x dash plus xy dash. Now over here it will be x dash y plus y dash, and we know that x dash is 0, xy dash will remain, x dash y will remain, this will also be 0. So this will ultimately, anything odd with 0 will give me the same thing back. So it will be x dot y dash plus x dash y, and this will be exclusive odd, x exclusive odd with y. So using just 4 gates, I can realize an exclusive OR function. But note that it will be a 3-level implementation. It is not a 2-level implementation, right? But in that sense, this was also a 3-level implementation, because if the complements are not available, so you have to generate the complements first. So that way, this circuit becomes more advantageous as far as exclusive OR implementation goes. So after having seen this slide, let us now move on to the design of a half adder. First, we will see half adder, and then we will see how is half adder different from a full adder. So this is the truth table. Essentially, if I'm not taking the carry in as one of the inputs, it will become a half adder. So it is essentially x plus y. So when both of them are 0 0, the sum is 0 and the carry is 0 also. When x is 0 and y is 1, so 0 plus 1 will give me a sum 1 but a carry 0. 1 plus 0 will give me a sum 1 and a carry 0. Whereas when x plus y and xy are 1 1, so 1 plus 1 will give me 1 0, right? 1 plus 1 will be 2, which is expressed in binary as 1 0. So I'll get the sum bit as 0 and the carry bit as 1. So this is the truth table for a half adder. I can very easily implement it. C is xy, because both of them, x and y, they are 1 1, so it is xy. That is very straightforward. And obviously there cannot be any minimization possible either, because there is just a single one. So this one cannot be combined with anything, because there is no one, there is no don't care condition. So it will remain all alone. So it will be xy. Now coming to S, there are two ones, but again these two ones cannot combine, because this is essentially an exclusive OR function. Remember, this is the truth table of exclusive OR function, right? So S is equal to x dash y. I'll take the min terms corresponding to ones. So x dash y plus xy dash. So this will be the expression for the sum bit of a half adder. I can realize them. Xy dash plus x dash y, this is sum bit. Xy, this is the carry bit. Alternately, I can have the sum bit can be realized as x in the or and implementation. It can be realized as x plus y and x dash plus y dash. That is how it can be realized. This will remain xy. There are so many possible implementations of it, right? S is equal to c plus x dash y dash whole dash, and c remains xy. Over here c has also got changed. So these are the different possible implementations. You can check for yourself whether all these implementations are going to give me this basic expression or not. This you can check. This is what I was mentioning. S is nothing but the exclusive OR of x and y, because S is equal to x exclusive OR with y, which is nothing but x dash y plus xy dash, and C remains xy. So this may be the smallest possible circuit as far as the logic diagram goes. Otherwise, this exclusive OR in turn will have to be realized using one of these implementations, as we have seen earlier over here, right, in the previous slide. So but from the presentation sake or the logic circuit diagram sake, we can see that this is the smallest possible representation of a half adder. So I can draw a block diagram like this, in which I'll have an exclusive OR gate, I'll have the AND gate, the inputs are X and Y, the outputs are S and C, right? So remember, this is the simplest possible in terms of drawing the logic diagram. Otherwise, these implementations are there for you to check whether this implementation is all right or not. Now, coming to full adder. In full adder, I also have the carry in bit. So that way I have 3 bits now as the inputs. So X may be taken as the carry from the previous stage, and this may be the 2 bits to be added. Okay. So let us take the truth table. The truth table should have all the possible input combinations. So 0 plus 0 plus 0, sum is 0, carry is 0. 0 plus 0 plus 1, sum is 1, carry is 0. 0 plus 1 plus 0, sum is 1, carry is 0. 0 plus 1 will be 1 0. So a sum bit being 0 and a carry bit being 1. 1 plus 0 is the sum bit being 1 and the carry bit being 0. 1 plus 0 plus 1 is 1 0. So a sum 0 and a carry 1. 1 plus 1 plus 0 is having a 0 sum and a carry 1. It is when it becomes 1 plus 1 plus 1, I get 1 1, because that will be 3, which when represented in binary is 1 1. So in this case, the sum bit would be 1 and the carry bit would be 1 as well, right? So this is the truth table of a full adder. Now let us see whether it can be combined. So first of all, we will populate it for S. When I populate for S with 3 variables x, y, z, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So K map coming to our rescue, it will have 0, 1, 1, 0, right? That is how we count it. And then 1, 0, 0, 1. So I've got 1 at all these places. So we see that again, 1 cannot be combined, right? Because none of the ones are adjacent to each other. They are adjacent diagonally, but in diagonal we don't have the combination in K map. It has to be vertical or horizontal. So, and there is no don't care condition either. So the sum can be written as individual terms: x dash y dash z plus x dash y z dash for this term, min term, and then this is x y dash z dash. So that is how you can complete the expression for sum bit. Now for carry bit, let us populate it. This is the carry column 0 0 0 1. So 0 0 0 1, a 1 here, right? Then 0 1 1 1. So 0 1 1 1. Now combinations are possible, right? In fact, this combination is possible. So when I combine this, x gets eliminated, I get yz. This combination is possible over here, x, y gets eliminated, xz. So xz is here. Now this combination again, x and z gets eliminated, y. So I get xy plus xz plus yz. So minimization is possible in C, but there's no minimization possible in S. Okay. One thing I suggest that you do yourself, you can see that, check whether S is equivalent to X exclusive OR with Y exclusive OR with Z. Remember, in the previous slide I've shown, one of the previous slides, that I can the exclusive OR function is associative, right? So you check for yourself that this should come out to be X exclusive OR with Y exclusive OR with Z, done either way. By either way, I mean either you exclusive OR Y and Z and then exclusive OR with X, or you do exclusive OR between X and Y and then exclusive OR with Z. You understand? So, and in either way you will get the same expression. So that will also give you the verification for the associativity of exclusive OR function. And another thing that you will get to know, and which would be useful later, is that this can alternately be written as x exclusive OR with y exclusive OR with z, just as in the case of half adder, s was x exclusive OR with y. Over here it will be x exclusive OR with y exclusive OR with z. This is for you to check. I can realize these functions: x dash y dash z plus x dash y z dash, x dash y z dash, then x y dash z dash, x y dash z dash, then x y z, everything odd, I'll get sum. And C will be xy plus xz plus yz, all odd, you will get a C. So this will be the design of full adder, which will have a carry in bit in addition to what the half adder had, right? Another interesting thing, full adder with two half adders and an OR gate. So you see, this, if you remember, is the half adder, right? X exclusive OR with y and xy. This is another half adder. This is another half, right? So I'm employing two half adders and an OR gate. Now let us analyze. S. S is nothing but Z exclusive OR with X exclusive OR with y. This is X exclusive OR with y, and another exclusive OR with Z. So S is essentially Z exclusive OR with X exclusive OR with y. So I was telling you in the previous slide to check whether this is going to give me the same expression or not. So before you see my slide, try doing it yourself, right? If you're not able to, take help from here. If you're able to, that will give you the confidence. Anyway, for the sake of completeness, let me do it. Now I can write this as Z dash xy dash plus x dash y, because x exclusive OR with y is x y dash plus x dash y. So x dash y, let us do. So this is z dash, and then the truth form plus the true form of z and the complement of the other term. Now this is z dash xy dash plus x dash y. This is same plus z. Now let us apply De Morgan's theorem here. So when I apply the De Morgan's theorem, we know that the complement of exclusive OR is the exclusive NOR. So I have basically replaced this by the exclusive NOR function, right? So because exclusive NOR is nothing but the exclusive OR followed by a NOT function, and this is the expression of exclusive NOR we have seen earlier today itself, right? So as the next step, z dash xy dash. So I can write it xy dash z dash because of commutativity, and then x dash y z dash using distributive property, plus xyz, again distributive property, plus x dash y dash z, right? So this is how I get the expression for S, which is the same as we have obtained in the previous slide. So I can say that using half adders, two half adders cascaded by each other, you are able to get S comfortably. Now coming to C. Oh, in C, what I'm doing is X exclusive OR with Y ANDed with Z, right? So X exclusive OR with Y, this is the expression, this is ANDed with Z, right? Plus this is xy, right? The carry bit of it, as we've obtained in the previous slide. So I have ORed these two. When I open it up, it is xy dash z plus x dash yz, right? Plus xy, plus xy. Now you can see that over here I can take z common, right? In fact, that was there. So this is the expression for C as we have seen in the previous slide, right? This is the expression for C as we've seen in the. Okay. So I made the necessary correction in order to make things more clear. What I'm doing is I've obtained the term for S. That is all right. That coincides with what we have obtained earlier in the previous slide. For C, let us take help of the Carnot's map. I've got this by distributive property. I've got this. Let us populate this Boolean expression in the K-map, right? So I know that x y dash z means 1 0 1. So 1 0 1, that means this one will come, right? Now x dash yz, x dash yz means 0 1 1. So 0 1 1 is this one, right? So I've got this one from this term, I've got this one from this product term. Now how about xy? Xy means that x should be 1, y should be 1, and z should be varying. So I should get two ones corresponding to it, right? So x should be 1 and y should be 1 and z should be varying from 0 to 1. So x1, that means I'm talking about this row, and y being 1, that means I'm talking about this and this, right? where z varies. So these two ones will come from there, right? So this one comes from this one comes from this product term, and these two ones come from this product term. So this is nothing but the k map that we have obtained for the full adder, which in turn will give me c is equal to xy plus xz plus yz, as we've already obtained earlier. So this shows that using two half adders and an OR gate, I can realize a full adder as well, right? So that way this is a useful circuit. Now, coming to design a subtractor, a half subtractor, just like the full adder, a half subtractor will have 2 bits. So 0 minus 0, the borrow will be 0 and difference will be 0. 0 minus 1, there has to be a borrow, right? So when the borrow is 1, and when I take a borrow here, it becomes 2. 2 minus 1 is 1. So both borrow and difference will be 1 1. 1 minus 0, no borrow and the difference is 1. 1 minus 1, there is no borrow and difference is also 0. So this will be the truth table for half subtractor, which can be written as, you can see that D is the same as the sum in an adder, right? So D is x dash y plus xy dash, which is x exclusive odd with y, right? B is different from the carry bit of the half adder, right? Because B is, in that case, the carry was xy, but over here it is x dash y, x dash y. So this will be the expression for half subtractor. You can correspondingly translate it into the logic diagram correspondingly. Now full subtractor, it will have 3 bits as inputs and 2 outputs, borrow and difference. So this will mean 0 minus 0 minus 0, the difference is 0 and the borrow is 0. 0 minus 0 minus 1, there has to be a borrow. So when you take a borrow to it, it becomes 2, and 2 minus 1 is 1. So both borrow is 1 as well as difference is 1. Now 0 minus 1 minus 0, again a borrow has to be taken, so borrow bit must go 1. As soon as you make it 1, it becomes 2 minus 1, so the difference is 1 again. Now 0 minus 1 minus 1, again borrow has to be there. When you take a borrow, what happens? The difference is 0, because 2 minus 1 minus 1 will be a 0, right? So 1 minus 0 minus 0, there's no borrow and the difference is 1. 1 minus 0 minus 1, there has to be no borrow, but the difference will be 0. 1 minus 1 minus 0, again there has to be no borrow, but the difference will be 0. Now 1 minus 1 minus 1, there has to be a borrow, so borrow bit must be 1. And when you take a borrow, it becomes 3. 3 minus 1 minus 1, that will be 2. 3 minus 1 minus 1 will be 1, so the difference will also be 1. So that is how you can write down the truth table for full subtractor. Then you can make use of the uh, K maps corresponding to D, corresponding to the borrow, and when you do it, you populate them 0 1 1 0. So 0 1 1 0 and 1 0 0 1. You see that they cannot be combined. None of them can be combined, so you'll have to write them in full. The first term will be x dash y dash z. That is how you get it. This one will be x dash y z dash. So x dash y z dash. This one will be x y dash z dash, and this one will finally be x x y z. So this will be the expression for the difference. For borrow, 0 1 1 1. So 0 1 1 1 and again 0 0 0 1. So 0 0 0 1. So you see that over here this was no different from the sum bit of a half adder. Similarly, the difference bit of a full subtractor is no different from um, the sum bit of a full adder, right? But this will be different because now they will combine. So when you combine them, you see that x dash y gets eliminated, z x dash z, this term, right? And then these two x dash y, right? X dash y, this one, and then finally over here it will be x will be eliminated by z. So these are the expressions corresponding to a subtractor. So that is how you can design a half subtractor and a full subtractor as well. Now parallel adder. Till now what we have seen is addition of a single bit, right? Two single bits are given, plus maybe a carry bit in the case of a full adder. Now, what if I have to add like 4-bit numbers, two 4-bit numbers? One is A, which is equivalent to A3, A2, A1, A0, right? And then there's another one, which is like, okay, let me, okay, so this is a parallel adder in which we can add more than one bit. So let us first see the procedure. How do we do it? Suppose I'm given two numbers, two binary numbers of 4 bits each, A and B. So how do I add them? 1 plus 1 with a carry 0, with a sum 1 and a carry 1. 1 plus 1, a sum 1 and a carry 1. 1 plus 0 will be 1 with no carry, so 0. 0 plus 1 plus 1 will be a sum 0 and a carry 1. This is how we do the addition. Now a full adder is allowing me to do this much only, right? This much only. And it is giving me the sum bit and the corresponding bit. So what I'll do is, this is FA means full adder, right? So let me generalize the process. Suppose I have two 4 bit binary numbers, A with the bits being A4, A3, A2, A1, B being B4, B3, B2, B1. The corresponding sum bits are S4, S3, S2, S1, and the carry bits are C5, C4, C3, C2, C1. This is said to be the final carry, right? And this could be the input carry if it is coming from some previous stage. If it is not coming, we'll keep it 0. Just as we have kept 0 here, right? So in that case, I can keep it 0. So essentially, I have got the full adders employed like this. This full adder receives the carry bit if there is any coming from this side, and the sum bit that it is generating. These are the two bits that are to be added, A1 and B1, and whatever carry comes out, that goes to the next stage, right? Next stage along with this carry adds up A2 and B2 and gives me S2 and C3, right? Gives me S2 and C3 like this here, S2 and C3. This C3 will be the input carry to the next stage, which will get added up with A3 B3. The sum will be S3 and its carry generated will be C4, which will be the input to the next stage. And this C4 will be added up with A4 B4 to give me S4, the final sum bit, and this will be the final carry or the output carry, right? So this is, and note that this is a modular design. If I have to make it more than 4 bits, 5 bits, then I'll have to repeat the entire thing, wherein the C5 will be to the next stage, the inputs will be A5 B5, the output will be S5, and the carry that will come out of it will be C6. So whenever I stop, so I can use it using, I can employ it having n bit adder. I can call it n bit adder because the design is very modular. You just have to design one module and you have to keep replicating. Another thing that I want you to see is that the very first stage, if it is not receiving carry from any other stage, is as good as a half adder, right? So now you can realize the difference between a half adder and a full adder. This is pretty much a half adder if this C1 is not there, right? If you exclude this C1, then it will simply be A1 plus B1, you will get S1 C2. So this first stage can be a half adder, but for the sake of modularity, let us employ a full adder here too, with this C1 being grounded or being fed a 0 here if it is not coming from some previous stage. So this is how, it can be, we can design an n bit adder. Also, this is said to be a ripple adder. Why a ripple adder? Because you see these carries are rippling through stages. It cannot give the final S2 C3 until it receives C2. Similarly, it cannot give you a final S3 and C4 until these two stages carry out addition. So the results are rippling through, right? So after the final stage only, the final output will be available at all these points. So now suppose I store a 1 here, I give this 1 here, I give this one, this one over here as A2, this 0 as A3, and this 1 as A4. And I feed 1 as B1, 0 as B2, 0 again as B3, and 1 again as B4. And I give C1 as 0. I must get S1 0, S2 0, S3 1, S4 0, and these C2s would be C1 I've given 0 anyway, so C2 would be 1, C3 would be 1 again, C4 would be 0, and C5, the final carry, would be 1. So this is how, using full adders as the modules, what is inside full adder, that we have seen already, right? We have designed in the previous stage. So this is how you can have an n bit full adder, right? So let us stop here. From here on, we will see in the next slide, because these are the new topics that I've introduced today. So go through them thoroughly and try to understand the concept behind the addition process, right? Thank you very much.